From orbit, Europa looks dead, a frozen shell drifting through the dark, locked in Jupiter's gravity. No atmosphere worth naming. Surface temperatures that never climb above minus 160 degrees Celsius. Nothing moves. Nothing changes. Nothing lives. But the cracks in that ice tell a different story. Beneath Europa's surface, scientists now believe, lies a saltwater ocean 2 to 3 times larger than every ocean on Earth combined. An ocean that has never seen a single photon of sunlight. And on our own planet, that is exactly where life learned it did not need any. Europa's surface is not the smooth, silent plain it first appears to be. Up close, the ice is fractured, etched with dark lines that stretch for thousands of kilometers, crossing and recrossing the moon's face like the veins of some ancient creature. These are not scars from impacts or the slow work of time. They are fresh. The ice here reflects sunlight with a bond albedo of 0.64, making Europa one of the brightest objects in the solar system. But this brightness is deceptive. It is not the gleam of untouched snow, but the glare of ice that is constantly being broken, shifted, and renewed. Across the moon, the surface is stitched with double ridges, some as high as a city block, running parallel for hundreds of kilometers before splitting or vanishing into chaos. These ridges are often flanked by bands of darker material, likely salts or minerals brought up from below. In between, the ice is broken into blocks, some the size of Manhattan, jumbled and rotated as if they had drifted on a sea, then frozen in place. Scientists call these regions chaos terrain. The temperature here tells another part of the story. On the night side, Europa's surface plunges to 50 Kelvin, so cold that steel would shatter. Even under the weak sunlight of Jupiter's distant orbit, the warmest patches barely reach 110 Kelvin, far below the freezing point of water. And yet, the surfaces are young. Crater counts, the standard measure of planetary age, reveal a startling fact. Europa's skin is almost untouched by impacts. While ancient bodies like Mercury and the Moon are pockmarked and battered, Europa's face is nearly unscarred. The oldest regions are 60 million years old. Some areas may be far younger. This lack of craters demands an explanation. On a world this cold, where nothing should move, the surface is being erased and renewed. The ridges and chaos blocks are evidence of movement from within. Something is forcing the ice to crack, to shift, to open and close again. The patterns are too regular, too widespread, to be the work of random impacts or surface erosion. Instead, they point to a restless interior, an engine beneath the crust, unseen but relentless. Europa's ice shell is not a static barrier. Measurements from NASA's Juno spacecraft show that the shell is, on average, about 29 kilometers thick, but in places it may be thinner, especially beneath the chaos regions. The shell is likely layered, a brittle, conductive lid over a warmer, slowly convecting interior. Where the ice is thinnest, heat and perhaps even water can force their way upward, breaking the surface and leaving behind the telltale scars. The result is a world that looks dead from a distance, but on closer inspection, is anything but. Every fracture, every block of chaos terrain, every fresh, bright patch of ice hints at a world trying to break through its own skin. The mystery is not just what lies beneath, but what could possibly be driving such renewal in a place so far from the sun. Something under Europa's crust is stirring, and whatever that is, it has rewritten the face of the moon again and again, erasing the past and keeping its secrets locked beneath the ice. Magnetic fields, invisible but relentless, sweep across Europa as Jupiter's colossal magnetosphere rotates. In December 1996, the Galileo spacecraft drifted through Europa's shadow and captured a signal that would change everything. Its magnetometer detected a magnetic field that did not match Jupiter's alone. Instead, the field shifted and pulsed as Europa orbited, as if something inside the moon was conducting electricity and pushing back. Only a global salty ocean, tens of kilometers beneath the ice, could explain this magnetic echo. The data showed that this hidden sea must be at least several kilometers thick, stretching for hundreds of kilometers in every direction, and rich enough in dissolved salts to carry a current. The evidence did not stop there. In 2012, the Hubble Space Telescope turned its ultraviolet eyes toward Europa's southern limb. For a few fleeting hours, it caught a faint, ghostly column of hydrogen and oxygen, rising more than 200 kilometers above the surface. This plume of water vapor could only have erupted through cracks in the ice, venting material from far below. Later observations would debate the frequency and strength of these plumes. The original detection remains a powerful sign. Something beneath the crust is pushing upward, breaking through the frozen barrier. Gravity, too, tells its story. As Galileo flew past Europa, the spacecraft's radio tracked tiny wobbles in the moon's motion. These subtle shifts revealed that Europa's icy shell and its deeper interior are not locked together. Instead, the crust floats, decoupled from the core, riding atop a liquid layer. The shell drifts and rotates at a different rate than the interior, a phenomenon that only makes sense if a global ocean separates the two. Layer by layer, the case for water beneath the ice has grown stronger. Magnetic induction, gravity tracking, and plume detections each point to the same conclusion. Beneath Europa's fractured, brilliant shell lies a vast ocean, possibly deeper than any found on Earth. Calculations suggest this ocean holds 2 to 3 times the volume of all Earth's oceans combined. The surface is cold beyond comprehension, yet below, a world of liquid persists. The ocean's very existence demands a source of heat, one that can defy the darkness and the chill of deep space. The evidence is no longer a matter of suspicion, but of scientific confidence. The question now is not if there is water, but what that water might conceal. The ice is only a mask. The ocean waits below, restless and unseen. Jupiter's presence is never gentle. Its gravity is a force that dominates Europa's every move, a giant's grip that twists and pulls the moon in a relentless cycle. Europa does not orbit in perfect harmony. Instead, it is locked in a three-way dance with its neighbors, Io and Ganymede, each moon pushing and pulling the others into a precise 1 to 2 to 4 resonance. For every orbit Europa completes, Ganymede circles once and Io twice. This resonance keeps Europa's orbit slightly oval, or eccentric, so its distance from Jupiter is always changing. The effect is subtle, but the consequences run deep. With each lap around Jupiter, Europa is flexed like a rubber ball. The moon's icy shell and rocky core are squeezed and stretched by the shifting tides, rising and falling by tens of meters. This mechanical kneading generates friction inside Europa, and friction means heat that cannot escape easily into the void. Instead, it seeps upward, trapped beneath the ice, building an internal furnace that never cools. Estimates suggest that Europa dissipates between 0.1 and 1 terawatt of tidal energy, enough to power 1 billion homes on Earth, or to keep an entire ocean from freezing solid in the darkness. The heat is not spread evenly. It concentrates beneath the ice, especially where the shell is thinner or fractured. There the energy bubbles up, melting the base of the ice, driving convection and weakening the crust. These are the regions where the surface is most chaotic, where plumes erupt, and where the secrets of the ocean are most likely to break through. Jupiter's tidal grip is invisible, but its influence is everywhere, in the fractured shell, in the restless ocean below, and in the possibility that something, somewhere beneath the ice, is alive. The warmth of that hidden sea is not a gift from the sun, but the result of a cosmic struggle, gravity's unending pull, sculpting a world in darkness. Europa is a world defined by its scale, yet its most astonishing feature remains hidden. Beneath the jagged, shifting ice lies a sea so immense that it dwarfs our own. The ice shell, measured by Juno's microwave radiometer, averages about 29 kilometers thick, nearly 3 times the height of Mount Everest stacked end to end. But this is only the beginning. In some chaos regions, the shell thins to less than 15 kilometers, opening potential windows between surface and sea. Below this fractured crust, the ocean stretches for perhaps 60 to 150 kilometers in depth, encircling the moon like a dark, global abyss. Calculations based on Europa's radius and the measured shell thickness suggest a water volume of up to 2.5 billion cubic kilometers, 2 to 3 times the volume of all Earth's oceans combined. On a world barely a quarter the size of Earth, this is a staggering reservoir. If every drop of water on Earth were poured into Europa's ocean, there would still be room to spare. This ocean is not a shallow pond trapped beneath a thin glaze. It is a planetary sea, deep enough to swallow the tallest mountains on Earth many times over. The pressure at its base would crush a submarine, yet the water endures, kept liquid by the constant kneading of Jupiter's gravity. Microwave radiometry reveals the shell's layered structure, a brittle, cold lid above, a warmer, convecting mantle below. Where the ice is thinnest, the ocean draws closest to the surface, hinting at places where the two worlds, frozen and liquid, might touch. Europa is, in effect, a miniature ocean planet. Its surface is only the mask. The true world is the vast Black Sea below, silent and unseen, holding more water than any place we know. The scale is almost beyond comprehension. A hidden ocean, restless and immense, waiting beneath the ice. Far below the reach of sunlight, Earth's oceans harbor communities that should not exist. At hydrothermal vents, where the seafloor splits and scalding water erupts from the crust, life gathers in the darkness. There is no sun and no photosynthesis, only chemistry and heat. Yet here, microbial pioneers thrive in numbers that rival any surface bloom. Between 1 million and 100 million cells in every cubic centimeter of vent fluid. These microbes form the base of an entire ecosystem, drawing energy not from light, but from the chemical gradients created as hot, mineral-rich water meets the cold abyss. Chemosynthesis is the secret. Microbes at these vents feed on hydrogen, methane, and sulfide, using them as fuel to build organic matter. In turn, their dense mats support tube worms, shrimp, and other creatures, an entire food web anchored not to the sun, but to the restless energy of the planet itself. The heat flux measured at these sites from 1/10 to more than 10 watts per square meter mirrors the tidal energy calculated for Europa's most active regions. The chemical energy released by vent fluids, tens of thousands to millions of kilojoules per kilogram each year, creates a living oasis in the deep. It is the existence of these thriving, sunless worlds that transforms Europa from a cold curiosity into a true possibility. If a moon can offer water, chemical gradients, and continuous energy, even in darkness, then the definition of habitability must expand. The best precedent for life in Europa's ocean is not found on the surface of any planet, but in the black, pressurized depths of our own. The lesson is stark. Where energy and chemistry flow, life can follow, even in the dark. Europa's ocean is more than a reservoir of water. It is an experimental flask governed by the same fundamental rules that shape all living worlds. For life to take hold, 3 conditions must be met: liquid water, the right chemistry, and a steady flow of energy. On Europa, these are not abstract ideals, but measurable realities. The water itself is abundant, trapped beneath an ice shell under crushing pressure, between 100 and 200 megapascals, enough to keep the ocean liquid at temperatures from -5 to 0 degrees Celsius. This is not a gentle environment. The salt content, dominated by magnesium sulfate and sodium chloride, mirrors the briny depths of Earth's own oceans. Electrical conductivity readings from Galileo's magnetometer confirm a salinity of at least 0.1% by weight, enough to carry a current and support chemical reactions essential to metabolism. Energy is the decisive ingredient. 2 engines drive Europa's chemical power. Deep below, water reacts with iron-rich rock in a process called serpentinization, releasing hydrogen, a fuel for chemosynthetic microbes. At the surface, Jupiter's relentless radiation splits water ice, producing oxidants like oxygen and hydrogen peroxide. These molecules can migrate downward through cracks, creating a redox gradient, a chemical tension between fuel and oxidant that life can exploit. Calculations show that the combined chemical energy budget reaches between 10 to the 12th and 10 to the 13th joules per year, rivaling the output of Earth's most productive hydrothermal vents. Within this cold, dark sea, the basic requirements for habitability are met. Temperature, pressure, salinity, and energy all fall within the known limits for life. The question is no longer whether Europa's ocean could host life, but what form that life might take and how it might persist in a world defined by extremes. No one expects forests or fish beneath Europa's ice. The most realistic hope is something far smaller, a world of microbes clinging to life in the dark. On Earth, the oldest and most resilient ecosystems are built on metabolisms that do not require sunlight. In Europa's ocean, the main candidates are methanogenesis and sulfate reduction. Microbes could feed on hydrogen produced by water reacting with rock below, combining it with carbon dioxide to make methane. Others might use sulfate, abundant in the briny water, as an electron acceptor, reducing it to sulfide. These are not exotic processes. They drive entire food webs at Earth's hydrothermal vents. But even the simplest life needs more than water and energy. Nutrients, phosphorus, nitrogen, trace metals, may be scarce in Europa's ocean. Models suggest phosphate concentrations could be 1,000 times lower than in Earth's seas. Nitrogen, too, is in short supply, with only traces delivered by radiation or comet impacts. This scarcity could choke off any biosphere, keeping cell numbers low and growth slow. If anything is alive beneath the ice, its presence would be subtle. The first hints would come as chemical disequilibrium, an excess of methane, or a strange ratio of hydrogen to oxygen, out of balance with what simple chemistry alone would produce. These are called first-order biosignatures, patterns that could point to metabolism, but not prove it. Detecting them would be the first step, a chemical whisper from a hidden world, hinting that something below is breaking the silence. Radiation on Europa is relentless. Jupiter's magnetosphere delivers a dose of 5 grays per year, enough to sterilize organics in days and erase chemical traces of life almost as soon as they appear. Anything from the ocean below, if it ever reaches the surface, is quickly destroyed by this invisible assault. The ice above is no less formidable. At its thickest, Europa's shell is nearly 30 kilometers deep. Even in chaos terrains, where the ice thins to under 15 kilometers, the barrier is daunting. No human-made drill has ever reached such depths. The idea of a cryobot melting its way down remains a blueprint, not a reality. Any future probe must survive crushing pressure, extreme cold, and meet strict planetary protection rules to avoid contaminating Europa's ocean with Earth microbes. For now, the search relies on what can be sent today. Reason, a radar aboard Europa Clipper, will scan for hidden layers and brine pockets. Mass Specs, a mass spectrometer, hunts for organic molecules at parts per billion sensitivity, searching exosphere vapors and plume material. Soudier captures and analyzes dust grains blasted from the surface, seeking traces of salts and minerals. Themis, an infrared imager, maps subtle warmth, potential signs of eruptions or thin ice. Each instrument is built to catch the faintest signals of life, pushing against radiation and ice that work to keep Europa's secrets sealed. Right now, Europa orbits in silence, its ocean hidden beneath kilometers of ancient ice. Yet instruments on Earth and in space wait for the faintest chemical trace, the smallest anomaly. If life can emerge in such darkness, it would mean we are not the exception, but the pattern. The search is no longer science fiction. It's a question every generation must face. What will we do if Europa finally answers back?